So let's say that you are working at a hospital, and before leaving for the evening, the doctor leaves a note that says, give 2 ibuprofen every 4. Are there any problems with this kind of note? The answer that you should say is that this note is missing units. So when it says give 2 every 4, 2 what? 200 milligram pills, 800 milligram pills, 1 milliliter doses, and every 4 what? Minutes, fortnights, blue moons? So without these units, this number is somewhat meaningless. So for instance, if I told you that I traveled 7 in 3, what would that even mean? So while in many everyday cases we can pick up on these implied units using context clues, in science we always want to be explicit about the units that we're using. And so the units that we're using in science are usually going to be metric, or what are called the International System of Units, or SI units. But in America, for instance, and in a few other countries, they often use the English system. And so these are going to be different. So we don't want to mix up these two things. And so, for instance, we have 1 pound is equal to around 2.2 kilograms. A quart is slightly less than a liter, and these yards are slightly less than a meter, and we have that 37 degrees Celsius is about 98.6 degrees Fahrenheit. And we'll talk more in later videos about how to actually convert between these. And so in the English system, for length, the base unit is usually the foot. In the metric, it's a meter. SI units, which are in metric, but sometimes the base unit for it is somewhat different. But with the length, the metric base unit is meter, and the same for the SI unit, where for volume in English, the gallon is the base unit, the liter in metric, and the cubic meter in SI, where you can see, especially at a chemistry lab, a cubic meter is quite big, and so that would not be very useful in a chemistry lab. But in SI units, quite often for reasons used in physics, the cubic meter is the base unit. For mass, the English base unit is the pound. For metric, it's the gram. For SI, it is the kilogram. For temperature, the English base unit is Fahrenheit. Metric is Celsius. SI is Kelvin. And so Celsius and Kelvin are both very similar in the sense that a degree is, for lack of a better word, the same size, but they both have a different zero. So the zero in Kelvin is absolute zero. And then time for all of them, luckily, it's just seconds as the base unit. And so when we are measuring numbers, we actually have to use what are called significant figures. Measured numbers are, as the name suggests, numbers that are obtained when you actually measure something, so you're using some kind of instrument to actually measure something. And like I said, these will have significant figures, where exact numbers do not have significant figures, and so we can count those as being sort of infinitely accurate. And these are numbers that are obtained by counting something or from a definition. So, for instance, when we define that a kilometer is 1,000 meters, we can know that to infinite accuracy just because that is actually how it's defined. We didn't have to go out and measure a kilometer and discover that it was, in fact, 1,000 meters. And so some instances of this, so measured numbers, so something like measuring the height of a person or the temperature of the room or the weight of a textbook. Exact numbers, so if we wanted to count the number of ladybugs here, then we would have infinite accuracy on that because we just counted how many there are. And like I said, if we look at the number of grams in a kilogram, then that is just a definition, same with the number of seconds in a minute. When we are actually measuring something, we cannot go to infinite number of decimal places. So the number of decimal places we can go is based on what our instrument has. So for instance, if we have these 3 rulers here, and so we are measuring this wooden stick, and it lies somewhere between the 4 and 5, which are the smallest tick marks on here. So we're looking right there. We look at where this measures to, and so we can do an estimated digit of 0.5. So we can say that it's about halfway between those, and so we can only go to 1 past the decimal and say that it is about 4.5 centimeters here. Now, if we're looking at the second ruler, we see that it has smaller tick marks, and so when we are doing a measurement, the tick marks with the numbers are the ones that we are going to use for our units. And so this one is a bit above 4, so we start with 4 centimeters, but then we look at the fact that these smaller tick marks are 0.1 centimeters, and so we can go to the 0.5 there, similar to how we did in the first one, but now because we can look at where this lies between those two smaller tick marks, we can do another estimated digit, which in this case would be somewhere between those two tick marks. We look at where it is in there and we see that it's a little bit past halfway, and so again, these are estimated, which means that your answer may differ slightly than somebody else's, but for this one, we're going to call it 4.57. Again, if you put maybe 4.58 or 4.56, those would be fine. That's an estimated digit, but we are saying that because this ruler has these smaller tick marks, we can go one more place past the decimal than we could with that first one. And so the incorrect measurements on here would be if we just call it 4 centimeters or 4.5 or 4.6, because again, it lies somewhere in between those two smaller tick marks. And so that means we can go one more place past the decimal with it. And so that gives us 4.57 centimeters there. This last one looks like we are again without those smaller tick marks, and so that means that we can only go with those larger tick marks. And so in this case we want to go to that 3 there, but again we have that one estimated digit, and so in this case it looks like it's lying right around pretty much exactly on that 3, and so we'll call that 3.0 centimeters. And so remember, measured numbers are ones that you obtain when you measure something. These have significant figures, and those significant figures will affect your calculations. Where exact numbers are ones that we do not have to take significant figures into account, and so they do not affect our significant figures and calculations. And we'll talk in the next video more about what we actually have to do when we are doing calculations with significant figures. And so when we want to come up with how many significant figures a number actually has, there are a few rules for this. The first rule is that all non-zero digits are always going to be significant, where zeros may or may not be significant. So determining whether zeros are significant is going to become sort of the thing that we actually have to worry about here. And so if we have a number like this 0.000234 grams, and we want to determine if it's significant, what we can do is we can draw an arrow from the left side, so those leading zeros to the right until we reach the first non-zero digit. Then all the digits after the arrow are significant. Any zeros under the arrow are not significant, but we do not want to eliminate the non-significant zeros. So when we talk about significance in this case, we're using a very particular definition of it. So the zeros there are important, but they're not significant in this particular definition. And so when we have this number here, we put that arrow over the zeros until we get to the first non-zero, and so we see that we just have 3 significant figures here. But again, we don't want to drop those zeros because 0.000234 is not equal to 0.234, so we do not want to eliminate those zeros. Now, if we want to count significant figures when we have zeros after the non-zero numbers and we don't have an explicit decimal point, then again we want to draw the arrow now coming from the right going to the left, so all the digits after the arrow are significant, all the ones under it are not significant, and again we do not want to eliminate the non-significant zeros. So if we have this number, we put our arrow over it, that means we have 4 significant figures. But again, remember, we don't want to drop those zeros because this big number here with all these zeros is not equal to 1,294. So we cannot eliminate those zeros. So those zeros are important, but they're not significant in this very particular definition of significance that we're using. So now to go through a few examples. So how many significant figures does this following number have? And so we can use this arrow here. We go to that first non-zero digit there. So that is our 1, and we have 1 significant figure. So when there is no explicit decimal point, the trailing zeros are not counted as significant. Now, if we put that explicit decimal point right there, that means that we have to count all 3 of these as significant. And so an explicit decimal point makes all trailing zeros before and after it significant. So that means this has 3 significant figures. So again, now we're adding a 0 after that decimal point, and so we have to count all 4 of these as significant. So that means it has 4 significant figures, and that's because an explicit decimal point makes all trailing zeros before and after it significant. Now, if we have these leading zeros with an explicit decimal point, then those are not counted as significant. So this one has just one significant figure. So leading zeros after an explicit decimal point are not considered significant. Now, if we then add more zeros, these are still not going to be considered significant. So we're just counting this 1 as the significant figure. So this still just has one significant figure. But now if we have a 0 after it, we have to count that 0 as significant. And so this one would have 2 significant figures. So trailing zeros after an explicit decimal point are counted as significant. And again, if we just add another 0 here, that means we're adding another significant 0 onto it. So this one would have 3 significant figures. Now, if we put that 1 there before the decimal point, now we have to count all of these digits as significant, because now those are not trailing zeros between that first one and that second one. Those are zeros that are between two non-zero numbers, and so now those are counted as significant. And so that means this would count as 6 significant figures. And if we have a number that is in the scientific notation, so that looks like this, where we're multiplying it by 10 to some power, then all the numbers that are in that coefficient before the 10 to some power are going to be counted as significant. So even if we have zeros there, those would count as significant. So in a way, that's one of the ways that scientific notation is actually quite nice, because we just know that any digit that's shown in that coefficient is going to be counted as significant. So recall that when we are doing scientific notation, if we have something like this 52,000 right here, and we want to turn that into scientific notation, we have to move that decimal point. So 1, 2, 3, 4 places, and so that means we shifted the decimal 4 places to the left, and so that means we put a 4 in that exponent there. Whereas if we have something like this 0.00378, then we want to shift this 1, 2, 3 to the right. So when we shift it 3 decimal places to the right, that means we get a -3 in that exponent right there. And so if you recall from your math classes, this is how we actually come up with these scientific notations. And so here is some practice problems. I encourage you to pause this video, look through these, and try to fill in this table. So what you're trying to do is, if the number is not in scientific notation, you want to write it in scientific notation and tell us how many significant figures there are. If it is in scientific notation, you want to convert it out of scientific notation, and again, tell us how many significant figures there are. So I'll let you pause the video and then I'll go over this. So this first one here, we have this large number here where we just have 101 at the beginning. So we want to move that decimal place, which is an implicit decimal point right there. We want to move that 7 to the left. And so that gives us 1.01 times 10 to the 7, and that is 3 significant figures. This next one, we have 0.00129. So we want to move that decimal point 3 to the right. So that gives us 1.29 times 10 to the -3, and that is 3 significant figures. This third one here, we have 29,080, and it has an explicit decimal point, which means that we have 4 significant figures, and this one, we are moving that decimal place 3 to the left, so it's 2.980 times 10 to the third. The next one is in scientific notation, so we want to convert this out of scientific notation, so we have to move that decimal 4 places to the left. That's what that -4 is telling us. So that gives us 0.000301, and that has 3 significant figures. The next one, 1.2839 times 10 to the 5. So that means we need to move that decimal point 5 to the right. But again, that 0 doesn't show up in our coefficient in the scientific notation. And so that means it's not counted as significant. So when we count the significant figures, we do not want to include that 0. That means we do not want to put an explicit decimal point after it. And so that means it has just 5 significant figures. But anyway, that was everything I wanted to talk about in this video. In the next one, as I said, I will talk about how we actually use these significant figures in our calculations, doing multiplication and division and addition and subtraction.